The Elitzur Vaidman bomb tester stands as a remarkable thought experiment in quantum mechanics, ingeniously designed to probe the seemingly paradoxical possibility of detecting a functional bomb without triggering its destructive potential. Conceived by Avshalom Elitzur and Lev Vaidman in 1993, this conceptual setup masterfully employs the core principles of quantum superposition, wave-particle duality, and the fundamental act of measurement. At its heart lies a modified Mach-Zehnder interferometer, a sophisticated optical instrument that allows a single photon to simultaneously explore two distinct pathways. The experiment begins by sending a lone photon towards a half-silvered mirror, or beam splitter. This crucial component introduces the quantum phenomenon of superposition, compelling the photon to exist in a probabilistic state where it traverses both possible paths within the interferometer concurrently. One of these paths is directed towards the potential location of the bomb, while the other serves as an unperturbed control. The introduction of a functional, live bomb along one path brings forth the critical element of interaction. Should the photon, existing in its dual state, encounter the live explosive, the very act of interaction causes the bomb to detonate, and the photon is absorbed, effectively halting that particular experimental run. Conversely, if the bomb is inert, the photon passes by without any interaction, continuing its journey as if no obstacle were present. Subsequently, the two paths within the interferometer are recombined using ordinary mirrors and a second beam splitter. Finally, detectors are strategically positioned at the two potential exit ports of this second beam splitter. The outcome of the experiment hinges on which detector, if any, registers the arrival of the photon, thereby revealing crucial information about the bomb's operational status. The most striking outcome occurs when a photon is detected at the exit port that would ordinarily experience destructive interference in an unobstructed interferometer. In such a scenario, waves taking both paths would typically arrive out of phase, leading to their mutual cancellation and, consequently, no detection. The fact that a photon is detected at this dark port implies a significant deviation from this expected behavior. It signifies that the photon must have indeed traversed both paths simultaneously, as dictated by the principle of superposition. However, the absence of a detonation indicates unequivocally that the bomb along one of those paths must have been non-functional. This is the essence of interaction-free measurement. We gain knowledge about the bomb's presence, or absence, as a functional device without the photon ever directly interacting with it. Conversely, if the photon is detected at the other exit port, the result is less conclusive. This outcome could arise if the bomb was a dud and the photon happened to take the control path. Or, perhaps more surprisingly, if the bomb was live, but the probabilistic nature of quantum mechanics dictated that the photon took the path devoid of the explosive. Finally, the absence of any detection at either port strongly suggests that the photon took the path where the bomb was located,